In third semester calculus, you define the vector between 2 points in the plane as being a set of numbers called the components of the vector, which are formed by subtracting the coordinates of the endpoints minus the coordinates of the starting point. We'll do exactly the same thing, except instead of saying that v equals the changes in the coordinates, we'll say v, according to some particular inertial frame, has the numbers delta t, delta x, delta y, delta z as components. If we're doing 2 or 3-dimensional ordinary calculus, we omit the delta t. We write it this way because, as we're going to see, the things that we did in third semester calculus are a little bit too simple. We define the sum, difference, and multiple of a vector the way we did it back in third semester calculus. I want to make a point that's very important. Suppose that we're doing a linear transformation and we have only time and x coordinates. I'll say that the t bar is a times t plus b times x bar is c times t plus e times x. If you form 2 points and make the vector that goes between them, and then form the components of the vector in the usual way, I want to look at how the components of the vector will transform. After doing the algebra, it turns out that the components of a vector transform according to the same laws that individual coordinates do. That is to say, if x mu bar is lambda mu bar alpha x alpha, the components of a vector transform according to v mu bar equals lambda mu bar alpha v alpha. And similarly, if you are transforming components from the barred system to the unbarred system. In ordinary calculus, either in 2 or 3 dimensions, u dot v is the sum of the product of corresponding components. A reasonable question for someone to ask is, what kind of linear change of variables leaves this invariant? After doing much work, it turned out that L times L inverse equals the identity does it, if you're talking about ordinary geometry, or L times eta times L inverse equals eta if you're doing special relativity. As usual, you can think of a set of components like this as being split up into the sum of 4 vectors, and then because of the way we multiply a vector by a number, I could write this as component v0 times basis vector e0, which is 1 in the time direction and zeros every place else, plus v1 times e1. e1 is the basis vector that has a 1 in the x position and zeros any place else, and so on and so forth. e0, e1, E2 and E3 are the standard basis for a inertial reference frame. In fact, we'll call them the standard coordinate basis. If you use the fact that a basis spans the space and is linearly independent, we figured out a couple of things. Not only do we know how the components of a vector transform, but using logic, we were able to figure out how the basis vectors transform as well. As we said many times in the first semester, though, a vector is an arrow. It exists in 2 or 3-dimensional space. It exists in 4-dimensional space-time, but it is an arrow. You don't really need any coordinates, except for the fact that coordinates are very convenient to calculate with. So I could write v as the sum over alpha, v alpha, e alpha. These are numbers. These are the basis arrows. I could also write v as the components in the barred system, v mu bar, summed over the basis vectors in the barred system. And one can think to themselves, isn't this inconsistent? And the answer is no, because if you write down v using the barred expression, use the fact that we know all of the ways that components and basis vectors can transform, group the appropriate things together, lambda, mu bar upstairs, gamma downstairs. This is a number out of the matrix that we were calling L previously. Lambda, delta mu bar downstairs is an element out of L inverse. We are summing over mu bar. This lambda times this lambda summed over the mu bar is the Kronecker delta, lowercase delta, gamma. Then I have my v gamma and my e delta. If you use the fact that the Kronecker delta is 0, except when the indexes are the same, here the only thing that's going to give a non-zero term is when little gamma equals little delta. So you'll have 1 times v little delta times e gamma, e delta that is, which you can then write in terms of the alpha index if you feel like it. This way, I can see that I can express the arrow in terms of components and basis vectors in any inertial frame. One form is a linear function that accepts a vector as its input and produces a scalar, which is a number that depends only on your location, but not on the coordinate system or any basis or anything like that. We will write for one forms, instead of v with an arrow, we'll have p tilde. This will be our generic notation for a one form. The collection of all one forms forms a vector space itself, the so-called dual space, to the space that you started off with. It must have a basis then. We're going to make a special basis. Having cooked up the standard coordinate basis for the vectors, we're going to say that omega tilde alpha is the one form, so that when I feed one of the basis vectors into that function, I either get 0 or 1. I get 1 if the two indexes alpha and beta are the same. I get 0 otherwise. In textbooks, people often write vector v as measured in O, or one form p as measured by O, as the list of the components. This is a terrible thing because it makes it look like this and that are basically the same kind of thing, but they're not. A vector is written as the sum of its components times corresponding basis vectors, coordinate basis vectors. P tilde will write as the sum of its components times the corresponding basis one form, coordinate basis 1 form. Because of what we've said, if you do P evaluated at V, that's the same thing as P evaluated at V alpha E alpha, sum over the alpha, you see. This is supposed to be a linear function, so if I multiply vectors by numbers and add them up, that's the same as calculating the value of P tilde at E alpha, multiplying by the components and adding them up. But on the other hand, P tilde is P beta omega tilde beta. So this is V alpha P beta omega tilde beta V alpha, E alpha there. However, we've picked the basis for the vector space and the basis for the one form in a special way. Omega tilde beta E alpha is 1 if beta and alpha are the same thing, and 0 otherwise. So delta beta alpha. I'll think of grouping these two things together. I'm doing the sum over beta of P beta times delta beta alpha. The only time that you get something different from 0 is when beta is equal to alpha. You'll have P alpha, Kronecker delta alpha alpha, which is 1. So you'll have V alpha, P alpha times 1. The set of all vectors, V, form a vector space. They have a basis. We have defined the one forms to be linear functions from the vectors into the scalars, with P tilde V arrow is P alpha V alpha. But on the other hand, the space of all one forms is a vector space as well. It has a dual space itself. It turns out that for a finite dimensional space, the dual space of a dual space of a vector space is just the original vector space. So if I start off with the vectors V, form the collection of all one forms, P tilde, the V vectors are linear functions of the one forms that go from the one forms into the scalar. And the usual way you do this dual space thing is you look at whatever P tilde evaluated at V is and declare that V as a function evaluated at P tilde is the same thing. By a long argument, we figured out a wide variety of things. We already knew how components of vectors and basis vectors transform. By doing similar logical arguments, we were able to figure out how the components of a one form change and how the basis one forms that go with the given coordinate system transform as well. If I want to provide some detail work on this is very interesting. P mu bar V mu bar. This is going to be P evaluated at V or V evaluated at P using the components in the barred system. But if you do the same kind of calculation that we've done before, you find out that P mu bar V mu bar is P beta V beta. That says that this one form evaluated at a vector or vector evaluated at a one form is frame invariant. And notice I didn't say anything about these being rotations or anything. This is true for any invertible transformation L, with the lambda mu bar beta being the numbers in the L. Another thing you can do And this will apply either to x and y, or x, y, z, or even t, x, y, and z. I'll think of the position vector, which, like in Calc 3, we define to be the coordinates times I, j, and k, or x0, coordinate number 0, times e0, plus x1 times coordinate vector number 1, x2, e2, x3, e3. If you look at that, if you form partial derivatives, you get the basis vectors. The partial of r with respect to x0, partial of r with respect to t. These last three terms don't contain t. The derivative of that with respect to t is e0. Likewise, partial of r with respect to x number 1, that would be partial of r with respect to x. No x, no x, no x, you'll get e1. So another way to think about these coordinate vector basis is I'm getting the basis by taking the partial derivative of location with respect to coordinates. Even in more general situations, we will do this. If we obtain a basis in this way, we will call it a coordinate basis. We can then cook up the corresponding basis 1 forms, and it'll turn out that almost all of our ideas will work. As a sanity check, let's think about what E mu bar is. That's the partial of position with respect to x mu bar. When I go from this to this, I am just using the chain rule. This is the sum over alpha of partial of x alpha with respect to x mu bar times the derivative of position vector with respect to x number alpha. This quantity, partial of x alpha with respect to x mu bar, is, in this simple linear case that we've been looking at, lambda alpha mu bar. So this says, this new idea tells me that E mu bar is lambda alpha mu bar E alpha, with the understanding that alpha is an index of summation. If you want, you can show that all of our other formulas still work the same. So another way I can think about these basis vectors is they're just partial derivatives of the position with respect to one coordinate or another. Now that's all very nice, but there is no such thing as a free lunch. There's going to be a catch attached to all of this. Suppose we build our basis vectors in this way. Then E alpha is partial of r with respect to x alpha, and E beta is the partial of r with respect to x beta. If I take the partial derivative of E alpha with respect to x beta, that'll be the derivative with respect to x beta of that. It'll be the second derivative of position, first with respect to coordinate alpha, later with coordinate x beta. If this is E beta, then partial of E beta with respect to x alpha is the derivative with respect to x alpha of that, which is that. When we do ordinary partial differentiation, which we're doing here, the order in which you differentiate doesn't matter, so it has to be true that partial of E alpha with respect to x beta has to be the same as partial of E beta with respect to x alpha. If this is not true, then whatever the basis that you're using is not a coordinate basis in the sense that we mean. If you'll recall in the first semester, one of the things we did was we did some arguing in flat two-dimensional space using polar coordinates. X is r cosine theta and y is r sine theta. This allows me to calculate the basis vectors in polar coordinates. E1 bar, E in terms of the r coordinate, is the partial of this with respect to r, which is cosine theta I plus sine theta j. Pardon me. On the other hand, in polar, the second of my coordinate basis vectors will be partial of the position with respect to theta, that's x number 2 bar. I'll have negative r sine theta I. I will have r cosine theta j. So I can actually get some formulas for E r and E theta, as some people would write them. Do these two vectors satisfy the stated requirement? Now, on the one hand, the answer obviously has to be yes because of the way I cooked these vectors up. But on the other hand, I can do the derivative of this with respect to theta, the derivative of that with respect to r, and see if I get the same thing. This will be a verification. If you do the calculation, both of these new derivatives work out to be negative sine theta I plus cosine theta j. So the answer is yes. The E1 bar and E2 bar are a set of coordinate basis vectors, but you have to be careful not to be too clever. Here's our two vectors, our two coordinate basis vectors using polar coordinates. If you look at the first one, we're in the land of ordinary geometry now. The length of ER, or E1 bar, is cosine squared of theta plus sine squared theta, which is 1. Square root of that is 1. If you figure out the length of this vector, you find out that it's r, though. Many people are disturbed by that and think, that's weird. So what I'm going to do is, I'm just going to normalize this second vector. I'll divide it by r, and then I'll just have sine theta I, negative sine theta I, plus cosine theta j, and I'll have myself a nice orthonormal basis, meaning that the basis vectors are at right angles to each other and both have length 1. At first glance, that looks like a very clever idea, but if you do that, you basically have shot yourself in the foot. Let me explain why. So we'll change our basis vectors, that and that. This is a perfectly good basis. Any vector in the plane can be written as a linear combination of those, but it's no good. If I take the partial of this with respect to theta, I get negative sine theta I plus cosine theta j. If I take the partial of this with respect to r, you now see why we've shot ourselves in the foot. There's no r dependence now. The partial of E2 bar with respect to r is 0. The condition that this has to equal that is not true. That means those basis vectors were not produced from the usual procedure by which we cook up a coordinate basis. These two vectors form a basis, but it's not a coordinate basis. Now you think, well, who cares about that picky little detail? The mountain of formulas that we've developed all are predicated on the assumption that we started off with a coordinate basis. So if I go around start using these kind of bases, half of my formulas don't work anymore, and half of everything we did goes right out the window. So we have to be careful about the kind of things we do. But it gets worse. If we're using the usual Cartesian basis, the I and the j, the I and the j are the same vectors no matter where you're sitting in the plane. Cosine theta I plus sine theta j is a vector of length 1 that points directly away from the origin. So if I'm sitting here at this spot, E1 bar is that vector, but if I'm over here, it's that vector. If I'm over here, it's that vector. Likewise for the E2 bar, the basis vectors are not constants. That means if I drew a vector in some place in the plane and asked you what its components are, end minus start isn't going to get the job done, and worse than that, the result depends on where I'm sitting at in the plane. These two vectors are supposed to be the same. Sorry, I can't draw worth anything. One of them, though, has its initial point at Q, and the other one has its initial point at P. But if my drawing were better, you would say, oh yes, parallel, same direction, same vector. Vector v at P and vector v at Q are the same vector. If we wanted to be careful about it, in the case where we're using non-constant coordinate bases, I really ought to write this. V, the arrow, equals, not arrow here, not arrow with an O or anything. V equals the sum over alpha of the components of V as measured at point P multiplied by E alpha measured at point P, and then I would do the same thing here. Now, of course, the reason that people usually don't do this at this stage of the game is we're in a flat Euclidean plane. If you give me another point, any point, there is a straight line that passes through that point that's parallel to, say, this vector. I could start at the initial point, and thanks to the Euclidean parallel postulate, I could just make another point. This could be point R. V would also equal V at alpha at point R times E alpha at point R. But this is so obvious in the flat two-dimensional case, people frequently don't do this. On the one hand, this is going to lead us into huge problems, but on the other hand, this is going to how we're going to make the jump to curved spacetimes. If you were back in Calc 3, vector v is the x component of v times I plus the y component of v times j. If a person wanted to be picky about it, and eventually we're going to have to, you would say that the partial of v with respect to x1 is, here you've got a product. You take the first thing times the derivative of the second thing, plus the second thing derivative, the second thing, times, let me say this again, first component times derivative of I, plus I times the derivative of the first component. Then, second component of v times derivative of j, plus j times the derivative of v2 with respect to x1. But this is silly. I and j are constants, so this term is 0, that term is 0, and we get back what you said you were going to do back in Calc 3. The way we do the derivative of a vector is we just use the derivatives of the components. Likewise, the partial of v with respect to x2 would be this. So let's think of a vector. In any frame, any coordinate system, I can write it as the sum over alpha, v alpha, e alpha. Although if we really wanted to be picky about it, we should put in the location where we're evaluating at. If I want to look at the partial derivative of v with respect to x beta, it's the derivative of component alpha with respect to x beta times e alpha plus component number alpha times partial of e alpha with respect to x beta. If we were using either Cartesian coordinates or some other coordinate system where the coordinate axes were straight lines, that would be 0, and we would be back in the land of Calc 3. If we're in a curved space or in a curved surface, the parallel postulate won't work. The basis vectors won't be constants, and then we have some serious thinking to do now. If you look at the definition of the partial of E alpha with respect to X beta, it's the limit of something. It's the limit of E alpha at one spot minus E alpha at another spot divided by a scalar. Every one of those quantities is a vector. Vector minus vector divided by number is a vector. Therefore, the limit is a vector too. Partially E alpha with respect to X beta can be written as a sum of the basis vectors. The basis vectors that go with whatever point it is that you're talking about. So I'm going to have some number that's going to have an index gamma on it so that I can do the Einstein summation convention here. Also, I'm specifically taking sorry about that. I'm specifically taking the derivative of basis vector number alpha with respect to coordinate number beta. So whatever I call this coefficient here, it's going to have a gamma in it, lowercase gamma. That lowercase gamma has to be upstairs so that I can use the Einstein convention. And the alpha and the beta, we'll think about what we want to make that look like. So I'm going to name this coefficient. This is the coefficient of E gamma in the partial of E alpha with respect to X beta. I'm going to call it capital gamma, lowercase gamma for the index of summation. The quantity with which I am differentiating with respect to has index beta. I'll write that second over here. And the only other place I have to put the other index in, the alpha is downstairs on the E, so I'll put it downstairs on the capital gamma. So what this tells me is the partial of a vector with respect to x number beta is what you would get if you were doing Calc 3 plus V alpha times capital gamma, little gamma alpha beta E gamma. One thing you could do is, in this first term, alpha is an index of summation, so as long as it doesn't conflict with anything else in that first term, I can relabel the alpha to be gamma, which I do, The reason I want to do that is the index on the E vectors are the same now. Partial of V with respect to x beta is a sum over gamma of some numbers times E gamma, and these numbers, partial of V gamma with respect to x beta plus gamma gamma alpha beta V alpha, that's the true partial derivative of the vector V with respect to x beta. This is usually called the covariant derivative. Sometimes people will take this individual number, the one with the beta, and write it as a gradient symbol with a beta of V. Or sometimes they'll even just leave the V off because you might want to do this to more general things. Commonly used notation is if you want to take the ordinary partial derivative of some quantity with respect to x beta, it's commonly seen that you'll write the quantity down and then a comma and then the index of the x with respect to which you're differentiating. So using the comma notation, this is partial of v with respect to x beta. The quantities that are inside the bracket are very often abbreviated as V gamma upstairs, no kidding, a semicolon, and a beta. So using that notation, partial of V with respect to x beta is V gamma semicolon beta E gamma. These are the components of the covariant derivative of V. This is the derivative that takes into account not only do the components change, the basis vectors can change also. These gamma numbers, these gamma gamma alpha beta numbers, are called Christoffel symbols, and they're very important to us in a wide variety of contexts. I'm going to stop here because I'm trying to keep each one of these things fairly short, but obviously I'd like to be able to figure out these Christoffel symbols, these capital gamma number, especially if I'm in a nice coordinate basis. We had about 4 different ways to do that from the first semester. After we clear that up, we're going to talk about tensors. A tensor is a function. An M n tensor is a function that takes a collection of vectors, n of them, and a set of one-forms, m of those, produces a scalar, and on top of that is multilinear. But I'm going to stop right there for today.